know that skin depth is the distance. Oh, I forgot to mention to you. Skin depth is the distance. And sorry, someone asked me what's last week. Someone asked me what's the dimension of alpha. I just found out what's the dimension. Alpha, the units of alpha is called meters per meter, okay? Meters. Meters per meter. Alpha is meters per meter. Okay? And skin depth is just 1 over alpha. So the depth that the wave needs to travel for its magnitude to reduce by how much? 37%, right? 37%. Right? Or basically is 1 over E. Alright, of the original. Okay? Oh sorry, 1 over E is 2.7. So it's the distance that you have to travel for the wave to decay to 37% of its original. That's the English of it. Do you get the English? Yeah? Okay? It is a distance travel in a lossy media, right, for the magnitude of the wave to decay by 37% of its original magnitude. That's very English. Alright, and then, so as it works out, in order for this to decay by 37%, it's just basically this divided by the E, right? Divided by 2.71, right? So in that case, what is Z that gives you 1 over E? So Z must be 1 over alpha. So that's why the skin depth is 1 over alpha. Alright? And alpha is meters per meter, okay? Okay, then we talk about good conductors, and we talk about good conductors, we talk about good conductors, and we talk about good conductors. And the characteristics of a good conductor is that we now take gamma equals to what? We drop off the complex term, we drop it out. Okay? Drop out the complex term because this is too small compared to that term here. Right? cable. So the cable length is how big? So let's say you have a twin conductor cable like this. Twin conductor, right? Twin conductor. Okay, now if the twin conductor's length, so for example, if the length of the twin conductor is so short, okay, so compared to the wavelength, it's so short, okay, so that means that the wavelength of your wave is much longer than the physical length L. So this is L, right? So the wavelength is much longer, right? Of your wave is much longer than your L. L is what, okay? But sometimes your cable length, right, for some reason or so, your cable length can be very long. Okay, your cable length can be very long. So you can see that, you know, we didn't. So this is C equals 0. This is C equals to L. Okay. So normally when we say when the cable length is long, we always, you know, we don't take a tape and go and measure and say, oh, it's very long, right? It's always long with respect to what? Long or short with respect to what? With respect to your wavelength lambda, okay? To that frequency of wave you are putting into that cable. Alright? So when I say the cable length is short, it means it's much smaller than the wavelength of, you know, than the wavelength. When I say the cable is long, that means to say that if I take a snapshot of this wave, right, on this cable, I'll get different magnitudes on this cable. Okay, so if I use a long cable, right, so from here I take a snapshot, so basically I will find that, hey, here, around here, the E wave is very strong, you know. Then, around here, the E wave is very strong, you know, in the positive. The E wave here is very strong. Then around here it becomes 0, you know. Then along here, the E wave is very strong, but now in the negative. It's now in the negative, right? It's now in the negative. All right, negative, and after that, it becomes 0 here. Then after that, if you continue on, right? It becomes very strong, here. Here is 0 again, nothing. Then here becomes very strong, and then after that, here becomes. Here becomes very negative. Okay, so here becomes very positive. So here is very positive, then here becomes very negative, after that here becomes very positive again, and here becomes very negative again. Okay, so if your length of your cable, correct? So let's say your cable terminates. So let's say I draw the cable. So if I terminate your cable here, let's say my cable terminates at this point, right? And then this point leads to the next circuit. This is the next circuit. So this is circuit A. Okay, and this is circuit B. You see it? This is circuit A and this is circuit B, right? And I'm using this to carry something across to that side. Alright, I'm using this as a wire to carry to that side. You see what's the problem that I'm getting? At circuit A, I put a high wave, right? But then at circuit B, because I terminate where this point is, what's my magnitude of this wave here? 0, you know. It means the high wave I put here is not going to go there, you know. So I put a high wave here, I get 0 there, you know. Then you look, hey, how come I put high here? should, right? 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 If I put a clock signal, if this is a clock, right? I put high, I should get high. Huh? But I put low, I should also get low. Clock, right? I put high, I get nothing, man. Zero voltage. Then later on, 1 second later, I get high again. Yeah, because why? This one will move, this one will move, right? Huh? This one will move, This guy here also will move, remember, this guy also will move, Okay? This guy will move, So straight away at the instantaneous snapshot, you put high, you get 0 here. And this one will move. So eventually this one will okay, we're looking from here, right? It's 0, right? So later on, what you get is it's inverse. So you put positive here, you get negative there. Right? And then over time, you get your 0 again, and after that you can become positive again. So it's weird. Right? How come I circuit like that one? So in transmission lines, you must understand, right? Your this wire is no longer a wire. It's got something in it. Alright? Because the physical length of the wire is what? Is of the same size as what? Very big, right? Bigger than the wavelength. Okay? Okay? Alright? It's bigger than the wavelength. Now the only way for it to act as a wire is when what? In order for it to act as a wire, what must you do? You got to shorten the length so that it's much smaller than that. Understand? You got to shorten the length until it's very small, until it's like a small little minute thing compared to the wavelength. Okay, so that it becomes a wire. So a wire is a wire when the physical length is much shorter than the wavelength. Okay? Something that you must understand. Okay? So we're always comparing with the wavelength. In the transmission line, we cannot assume the signal in the cable is of homogeneous strength. Homogeneous means exactly the same throughout the length of the cable. Instead, we now have to take into account the wave nature of the AC signal, and the cable is no longer called a conducting wire. Right? It's no longer called a conducting wire anymore. It's no longer a wire that connects two points on your circuit board. It's now a special transmission line. Well done. Right? In transmission line, the wave nature of the signal is taken into account. Wires, right? Because it's electrically short. They call it electrically short. Electrically means compared to the wavelength. Alright? Electrically short. In wires, we don't account for this wave nature because it's much shorter than the wavelength. Okay, we take a break. Come back 10:05. Alright? Come back 10:05.
Oh yeah, I think so. Oh, you can't base, yeah. So full. How can like that?
I'm hungry now. Very sad.
Okay. The example just now also shows something that I forgot to tell you. I better tell you now. Just now we were saying that this is alpha exact, alpha good conductor, right? Can you see another trend between alpha good conductor and alpha exact? Can you see that? What's the trend? Which is always higher, which is always smaller? Can you see?
Over estimate.
Alpha good conductor is always the delta good conductor is compared to delta exact is what? It's lower, right? Because it's just 1 over that, right? Correct? So what does that mean? So if you use alpha good, as an engineer, if you use alpha good conductor, it means that it gives you some sort of approximation, right? What sort of approximation it is? Optimistic or pessimistic?
I use better instead.
Depends on what
It's
context.
actually a worst case, right? Okay. So that means to say that it gives you a what we call a very, very conservative, right? Very conservative calculation of what the wave will be, right? Because if you use exact, then actually the wave, right, will be what, right? Is that correct? Okay. Oh, the other way. Sorry. If you use alpha good conductor, it gives you a what's the other way?
Best case.
Best case.
Not the. It gives a higher bound approximation. Higher bound. Higher bound or lower bound?
High.
Oh, sorry, lower bound.
High.
Lower bound approximation.
Alpha is
I'm looking at the skin depth.
higher skin that better means lower alpha is better, which means
Depends. Also depends what you want.
you are more conservative. Unless you want
That
it
is
to
also a
go about that.
lower bound. Correct? It's a lower bound approximation of delta exact. So what you calculate with good conductor is slightly shorter than what you will get with using exact in terms of the skin depth. Okay, slightly shorter. So remember that. Okay? So if you want to get alpha exact, normally what we do is that we take this number, we multiply it, by 1.01 or something like that. Alright? You get something closer to your exact. Okay? Because it's a lower bound
In
approximation.
terms of shielding,
Okay? So you need to know what you're doing, alright, as an engineer. That, okay, if I use this one, okay, it makes my life easier, but I know that this is actually a lower bound, right? Lower bound approximation, not a higher bound approximation. Okay, let's move on to transmission lines. Okay, so here's the difference between a wire and a transmission line. In a wire, that means you conduct signals without any variations along the line. It means the wavelength of the signal must be much higher than your wire. Okay? Than the length of the wire. Alright, the order of length. So it must be much higher. For a transmission line, the wavelength of the signal is approximately the same as the length of the wire. Or the other way, the length of the wire is much longer than the signal, than the wavelength of the signal. What are the signal characteristics? Time varying, but spatially homogeneous throughout the wire because it's very short, right? Wire is so short, the wavelength so big, so it's the signal is carried through and through, right? From the end because it's so small compared to the wavelength. Okay, but for this it is not, right? It is time varying, but it is not, but spatially heterogeneous. Heterogeneous means different,
okay.
right? Right, heterogeneous throughout the wire. Okay,
Do you like what you're talking about?
okay.
I don't like.
The wave characteristics for wire is none. For transmission line, there is wave characteristics there. greater than 4 times the length of the wire. The other way up. Or lambda signal is less than 4 times the length of the wire. Right? Okay, so if your signal is 4 times the length of the wire, that means if the length of the wire is less than 1/4 of your wavelength, alright, you call this a wire. Okay? If you are less than 1/4, or your wire length is less than 1/4 of your lambda, okay, or quarter wavelength, it's less than quarter wavelength. If your wire is less than what if your wire is less than quarter wavelength, right, of your signal, then it's a wire. If your wire is more than quarter wavelength, it is transmission line. And if we talk about frequency, it's the other way, right? When lambda is large, it means frequency is low. And when lambda is low, frequency is high. The other way, okay? Okay, and if you want to see how to convert between frequency, anyway, you know, right? Lambda equals to, you can always convert, right? E equals f lambda. Okay, convert, right? And just remember, I use the word B, it's not C. Why do I use C? You'll see later that in transmission lines, E is very much smaller than your C. So your C is 3 times 10 to the power 8 meters per second, right? Plane wave in free space, right? Right? But then in a wire, in a transmission line, your B is typically of the order 2 times 10 to the power 8. So it's 2/3 of the one, right? So remember, a transmission line, B is less. So this is equal to B times 10 to the power 8 meters per second, right? This is of the order of 2 times 10 to the power 8 meters per second, right? This is the problem with a lot of people when they do transmission line, they go and use C, answer wrong. Okay? Alright? You should know that for transmission about 2, and we'll tell you how to calculate this velocity for transmission line, okay? We'll tell you how to do it. It's not 2 times 10 to the power 8. Okay, so with what I've explained just now, tell me, is this a wire or transmission line?
Wire.
So I have a transmission line, I put a signal in. I don't tell you the wavelength, I don't tell you the length of this. I have 2 voltmeters, one at the start, one at the end. Wire or transmission line? And I see that this, you know, the voltage, right, is dancing together, synchronized. Synchronized swimming. So is this a wire or? Yeah, it's a wire, okay? Wire, okay? Alright, in other words, this is like electrically short transmission line. Right? Electrically short compared to the wavelength, right? Electrically short. So this is a wire, right? Must be what? Obvious lah. Okay, the voltmeters don't conform to each other one, alright? Here is high, here is low. Right? There's some plane wave characteristics of this transmission line, right? This one must be a transmission line. So this is electrically long. these are the electrons. Okay, that's moving. Alright, so you have two conductors, one at the top, one at the bottom. Okay, it's an electrically long conductor. Okay, so you can see that the E wave, alright, basically, so as you know, so the top gets compressed, right? The electrons, right? For example, if you look at this point, right, electrons get compressed, and the electrons, as it gets compressed over this side, it gets expanded on the bottom. Okay. So where it gets more compressed, there's more electrons compared to over this side. Okay. So this side becomes more positive over this side. That's why the E field goes from the uncompressed one. You can see the E field go from uncompressed to compressed. So this shows you the E field. Right? This is the E field, electric field.
The arrows are electric.
The electric field, right? These are the electrons, the charges that's moving in the conductor. Right? So it's moving up and down. Right? So as the top is compressed, the bottom is expanded. Right? And vice versa. If the bottom is compressed, the top is expanded. Okay? So you get E fields that's of different intensity across this wire. Right? Now if you have E fields, you must also have what? What Maxwell say? You get E field, you also must have what? Magnetic field, H field, right? And it's what? Parallel to what? H field is what? Normally parallel to what? To the E field, right? So it's the E field, and also what? Orthogonal to what? Orthogonal to the direction of travel also, right? So where is the H field coming? What's the direction of the H field? From here, can you see it? It's either coming out or going in to the page. Okay? They didn't draw it, okay? So the H field is coming out or going in, depending on the direction of E. So the H field is either this way, going this way, right? The E field is going this way. Okay? Alright? And they're both traveling. I don't know how to do it. Like that. Traveling in the Z direction, okay? Understand? Right, they're traveling in the Z direction. Okay, so this is what's happening in the transmission line. So in summary, at low frequencies up to 500 megahertz range, of the wave on the conductor is what? C naught over square root epsilon r mu r. Okay? Can you see that? Alright? plane waves in free space is 1 over mu naught. So for plane waves in the media, in a medium, right, which is not free space, right, it is just B, right, equals to what? 1 over square root mu r mu naught epsilon r epsilon naught, right? Alright? And this is actually the same as C over square root mu r epsilon r. Can you see that? Because C is 1 over square root mu naught epsilon naught, right? So mu naught epsilon naught 1 over square root is just C on top here, right? So for copper media, right, it has definitely got a epsilon r, right? It's got an epsilon r definitely, right? The mu r for a copper track is what? Copper, is it magnetic? Not magnetic, right? Copper cannot, right? So mu r is for copper is what? 1, right? Okay? So with the epsilon r, you just take C divided by square root epsilon r. That will give you the velocity of the wave in the copper track. That's what I told you, right? It is not, right? So you can see it's around 1.78, about 2 times 10 to the power 8, right? 1.78, right? So I told you the velocity in the copper track is that. Okay. So the velocity, right, for the wave traveling on the copper track is 1.78 times 10 to the power 8. So there are two effects. Okay. So how they find the velocity of the plane wave is very simple, right? They find out what is the glass epoxy epsilon r 4.7. Okay, and then they take the average of 4.7 with the relative permittivity of free space. What's that? Huh? They take that, alright? They take the average of 4.7 and the relative permittivity of free space. What's that? 1. Okay? So they take 4.7 and the average of 1. That gives you 2.85. Alright? 4.7 average with 1 is 2.85. So that will be the relative permittivity, right, as far as the wave is traveling on the copper. Because the wave, you know, right, is traveling on the surface of the board, right? So it's exposed to air. At the same time, it's also exposed to the board characteristics, right? So the board characteristics is 4.7, right? And the air characteristics on top, as it travels on the board, is 1. So what is the overall? So the overall, we take the average. Okay, that's why it gives you an average of 2.85. Okay, so now you plug in 2.85 into this calculation, you get your velocity of travel to be this number, which is not 3. Alright, it is 1.7 times 10 to the power 8. Okay, so if the velocity of travel is this, right? So what it means is that digital signals propagating along this track will suffer a delay of 0.56 nanoseconds, propagating from one end of the line to the other. Okay? Right, so digital signals will suffer a delay of 0.56 nanoseconds, propagating from one end of the line to another. So the problem is this. So if the line is electrically long, and the line length is in the order of the signal frequency is very high, then there will be different signal levels and phase shifts along the length of the 10 cm line. Right? So phase shift describes data coming from A to B. So you want to do a clock, right? You want to clock A. Yeah, so A and B are synchronous. So you clock A so that when A creates the data, B also creates another data out. So you're doing a clock. This is a clock signal. You know clock, right? You guys have done this circuit before? So you clock out, right? So this will be your final data. Okay? So your A got some logic circuit, right? It produces an answer when the clock comes in. Right? It produces when the clock comes in, it produces an answer. And then the clock is the same. So these are all synchronous clocking circuits, right? Synchronous clocking circuits. So they are all synchronous, and you say that, oh, okay, since they are physically apart, I just use a wire to connect to the clock. Okay, so what happens? And your clock signal is 0.5 nanoseconds. So tell me what happens. And the delay of this is what? 0.56 delay, huh? Okay. So the delay of this transmission line is 0.56 nanoseconds. So tell me what happens. What's going to happen? Okay. So the question is this: when the H comes in at A, when the H comes in at A, when the first positive H, or for example, the first positive H comes in at A, what does B see? So when the first clock signal comes in, or the first H of A comes in, alright, at A, so A produces the data, right? But what does B see? Will B see a clock? No, right? Correct. Why? Because if the first signal come in, right, you will see the clock where? B only see the clock 0.5 seconds later. Sorry, 0.56 nanoseconds later, which is there, right? Correct? So basically what you see is this. So when A sees this H, right? When A sees this H, correct? B will be seeing where? B will be seeing 0.5, right? 0.56. So B will be seeing this H, right? 0.56 meters, 0.56 away. Right? So when A sees this H, B will be seeing this part. You understand? Okay? When A sees this part, you will be seeing this part, right? Okay, still okay, right? Still okay, because positive, they get clocked, alright? Okay, still okay. But then you see that this is 0.5, this is 0.56. They don't match, right? They don't match. Correct? So what will happen? Right? Eventually, as time passes, as more and more time, right? Your B and B, right, will eventually, right? Eventually, when your A, so eventually, right, these two don't match, right? They are not multiples of each other, right? So eventually, what will happen is that you will find A on top and B at the bottom. You understand what I'm trying to say? Correct? So they cannot be, they'll not get synchronized anymore. Alright? They'll not get synchronized anymore. You'll lose the time. So is this a good transmission line for this sort of clock signal? Is it? No, right? So what can you do with this? You should shorten the, right? You should bring A and B closer together, right? So that when the clock comes in at A, if you can bring it shorter, then if the clock comes in at A, right, B will see it almost similarly at the same time. You understand? Okay? Alright? So this is the issue with high-speed digital signal. your delay of the line is of similar time, right, is of similar magnitude to your period of the clock, it's useless. Understand? Useless. Okay, now let's look at types of parallel conducting transmission. Okay, there are many types of parallel conducting transmission lines. So here are just some examples just to tell you. You have what we call the metallic waveguide, and this is used for microwaves. Right? So what will happen is that there will be variations on top here. Okay, there will be variations on top and the bottom, right? So that creates E fields, right? Going down, right? Alright, going down, alright? So that's for microwaves. This one is a coplanar waveguide. The next one is a coplanar. So you have, so this is your main conductor, this is your ground, that's your ground. So your E fields will go up like that. This is your E field, right? And then it will be traveling this way, right? It will be traveling this way. So this will be your E fields, alright? And then if your H field will be circular. Okay? So this will be your H field, circular. Cable. Coaxial cable is that you have a main conductor in the center, and then the outside is ground conductor. So your E fields will be this sort of gas already. Your E fields like that. Okay. And then your H fields will be circular, either clockwise or anti-clockwise. Okay. You can also have what we call a twin conductor, right? So one conductor is normally the active conductor, the other one is ground. So one active, one ground. So your E fields will be right like that, or this way, or this way, or that way. Right, like that. Then your H field is circular. Right, so your H field is circular. Another one. Okay. Well, you can read about all this. I'm not going to go through it. What are the usage of these things? Right. So the rectangular waveguide is used as for high frequency horn antennas, for example. Alright, used in very high frequency in the gigahertz range kind of applications, 30 to 40 gigahertz. Right. Then the coplanar and microstrip lines are used for microwave circuits. We call it MMICs, monolithic microwave integrated circuits. Okay. This one, right? So this is more for 30 gigahertz, 40 gigahertz. This is around 3 to 10 gigahertz, right? And then this one is maybe in the megahertz range. So this one is probably also in the megahertz range. So you can see that this is the, so you can say about 30 gigahertz. Right, this one is around 10 gigahertz. Right, and this is around megahertz. Okay, so you have different types of parallel conductors for different types of frequencies, alright? They all have their shortfalls and they also have their loss characteristics. So these are all copper wires. Okay. Let's look at the derivation, alright, to show about transmission lines. We're now going to look in the details of transmission lines. How we show that, or how we create, or how we have the wave characteristics in a transmission line. Alright, the mathematics behind it now. Okay, so this is the part for the derivations to show that it's actually like plane waves. So consider a two-conductor transmission line shown in figure 4. Conductors are parallel to the z-axis. Alright, so we apply a voltage between the conductors at the start point, right? So there's a voltage here. Okay, so if we apply a voltage and we assume that this is a transmission line, so it's going to be electrically long, alright? We assume it's going to be electrically long, it's not a wire. So when you apply a voltage, right, it's an electrically long thing, so there are certain parts. Oh, I think I made a mistake. I gave you a revised copy, right? So it's the E fields pointing in the right direction.
Yeah, right.
From plus to negative. Everyone got it the other way, negative to plus. If you got it from negative to plus, it's wrong. I've already given you a revision for that already. So it's from plus to negative, right? Okay. So you can see that in the animation just now, right? You create variations in the flow of electrons on both sides, right? So the E fields will be something like this. Okay. Now since the two conductors has got charges at different points of the thing, right? So what we can say is this, right? This suggests that line has a distributed capacitance. Per unit length. Okay? What I can say is this, since the charges at different points of the length is some positive, some negative, some positive, some negative, what it means is that there must be a capacitor there to store these charges, right? To allow these charges to be some positive, some negative, some positive, some negative, isn't it? Because what kind of circuit element can store charge? Capacitor, right? That's the only thing that can store charge. Correct? There's nothing else that can store charge. Correct? So, and the capacitor, there must be some distributed capacitor. That means each part where the charges can congregate, there must be a capacitor there. Alright? Where the charges can congregate, there must be a capacitor there. So there must be a capacitor here, 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 here. Everywhere along the line there is a capacitor. Right? There also must be some capacitor here, 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 here. Right? To allow you to store charge, right? So positive, negative means that there's a capacitor here. Right? It's like a parallel plate capacitor. Then another positive, negative means another capacitor here. Another positive, negative, another capacitor, another capacitor, another capacitor. So a transmission line is many capacitors together. Right? Okay. Okay. Now, when the charge is moving, right, there is also, it means that current is also moving, right? When charge is just the movement of electrons, right? So there's also currents moving in and moving out. Okay, a current, because of negative to positive, current moves from positive to negative, and then positive to negative, there's a current moving from there. Correct? So, and then here also, right, you can see the current moving and moving out. Alright, you can sort of see. So what kind of element stores current and allows current to move in and move out? What type of element? Inductor, right? Alright? So there must be an inductor here, inductor here, inductor here, inductor here. Correct? For this currents come in and come out. That's the only explanation you can find. Okay? So the result of a transmission line is that we have when you see a transmission line, don't see two pieces of wires, alright? See this. I want you to immediately, straight away, take your mind off two wires and straight away say that, hey, it's a capacitor, inductor, capacitor, inductor, capacitor, inductor, capacitor, distributed throughout the whole line. Alright? L is the inductance per unit length. So if L times a small change gives you the inductance, right? And C is the capacitance per unit length. So C times the length gives you the capacitance for a small length. Okay? And delta Z, right, is some small length that can approach zero. Alright? So that's what it means. Now there's a caveat I need to tell you. Caveat means condition. Caveat says this. Transmission lines have, in addition, inductance and capacitance, which you saw, right? You also have conductor losses, right? And what type of elements, right, will suck power off and you never get it back again? Resistors, right? Resistors are the ones, right? So you have a resistance per unit length as well. And all conductors, whether it's metal or copper or aluminium or silver, it has got a finite non-zero resistance, and the medium surrounding the conductor has loss in its dielectric. So your epsilon, so you have a dielectric, there's also got losses as well. Right? So you have a dielectric between, from here and here, there's an epsilon, the dielectric. The dielectric will absorb some of your power that you put onto the two conductors, right? You have loss, you have leakage, leakage. So if you run a high frequency, PCB, right? You find that your board is very hot, right? And this is because of the leakage into your material. Okay? So you have leakage. Usually this represents second order effects, right? And great thing for this course,